Hello, my name's Quinn, and today we're going to be talking about the concept of time complexity as it relates to computer programming. Well, to start off, what is time complexity? Time complexity is a way to mathematically measure the efficiency of a program or an algorithm. How is time complexity measured? Well, time complexity is measured by creating a formula or an expression that expresses the amount of steps or operation it takes to complete a program. Say that we have this list here. This list is a 5 integer list, and say that we want to write an algorithm that will search this list and find a given integer. Well, how can we do this? I think the first idea that would come to mind is to use a loop to iterate through each integer in the list until we get to the given integer that we want. Well, how could we convey how long this takes to run? You might think that you would want to find a way to calculate the amount of actual time it takes the program to run. This is incorrect, however, because we want to come up with a way that effectively demonstrates the efficiency of the program. And if we're calculating our efficiency based on time, then we might get a different outcome depending on the kind of computer we're running it on. If you're running this program on a very high end computer with good hardware, it would take a lot less time than if you're running it on something that was a lot slower. And because of this, varying time, we don't want to use this as a way to express the efficiency of this program. Instead, what we want to do is look at the amount of steps it takes this program to complete. So back to this algorithm we were talking about. If we wanted to write an algorithm that could search through this list and find a given integer, well, we would want to loop through it. And basically, we would want to just check each integer in the list until we find the integer that was the target integer. Well, there's a couple different outcomes that we could have, right? Because say we're looking for 4. Well, this would be what's known as the Omicron outcome. Omicron is a Greek character that looks kind of like this. And what it conveys in the um, related to time complexity is worst case scenario. So if we were looking for 4, that would be our worst case scenario. There are some other situations too, though. Say we're looking for 0. Well, if we're looking for 0, that would be our best case scenario or our omega situation. And if we're looking for like 2, well, this would be our theta situation or average case. But when we're talking about time complexity, the majority of the time we're going to be referencing the worst case scenario because when we want to express the efficiency of our program, we don't want to rely on luck or things like like how the array is sorted, but rather we want to convey what's the worst possible amount of operations that it could take this program to run. So let's now that we've talked about the different characters, let's show you an actual example of a time complexity expression. So for our example of a loop that iterates through each integer in the list till it finds the given target integer, our time complexity would be O of n. We'll draw a graph on the right here so you can see this compared to some other time complexities. This is what's known as a linear time complexity. It would look something like this. If we have size of the program on the x and the amount of steps it takes or operations it takes to complete the program on the y, well, given a linear time complexity such as O of n, we would have a directly proportional amount of steps to the size. So the size being the length of this array, 5, it would take us 5 steps to finish the program. Now let's go ahead and look at this in the code editor. I've written up a couple functions to try to help demonstrate these different concepts. And the first one I've written is linear time complexity. This is a simple function that takes an input of n and loops through n and prints each step along the way. So if we run this function with an input of 10, how many steps do you think it would take to solve this problem? Well, it would take 10 steps because we're going to be looping through the size of our input and printing each step along the way, meaning that there would be 10 iterations of this loop. So this is a good example of an O of n time complexity or a linear time complexity. The next thing I want to look at is what's known as quadratic time complexity. O of n squared. So a quadratic time complexity looks something like this. As the size of the problem increases, or the length of our array, the amount of steps it takes to find our given integer or to finish the program is going to increase quadratically. This is going to be a less efficient algorithm than our linear time complexity, because as the size increases, the steps are going to increase more dramatically than in our linear time complexity. So let's go ahead to the editor and take a look at an example of a linear time complexity. Or sorry, a quadratic time complexity. So here's our quadratic time complexity function. Again, it takes an input of n, but this time, instead of just looping through n once, we're actually using a nested loop. So this is our outer loop, this is our inner loop, and what's going to happen is our outer loop is going to run n times. But each time our outer loop runs once, our inner loop is also going to run n times. How many steps do you think it would take for this program to finish? 100 steps. Our for loops in Python start counting at 0, so what we really have is 99 here. But you can see the message I'm trying to convey. Basically, because we have two nested for loops, and they're both using n as the range, it's going to have n times n amount of steps. This is an example of a quadratic time complexity. Instead of the size and the steps being directly proportional to each other, now we have a quadratic relationship where the size is going to be quadratically related to the amount of steps it takes. So the last one I want to look at is O of log n. Now this one is a kind of confusing expression to explain, but basically what's happening is as the size of our problem is growing, the amount of steps it's taking to complete the problem is growing neither linearly nor quadratically, but logarithmically. This is an example of a more efficient program than the prior two. This is very powerful when you have huge sets for your input size. So if I had, a 1,000 integer long array, the amount of steps it's going to take is actually not going to be that much more than if we had a 5 integer array. It will be more, but compared to an O of n or an O of n squared time complexity, it's going to be a lot less. So I've written a function called logarithmic time complexity to help demonstrate this. What we're doing here is implementing a binary search type of algorithm. So what we're doing, and I think it would be best explained in the editor, the paint editor here, is we're taking our array and we're slicing we're indexing into the middle of our array. And what we're going to do is index into the middle and store it in a variable called guess. Now, the next step would be to compare guess to our target. So if guess is less than our target, then what we want to do is we're going to split the problem in half. So if guess is less than our target, then we're going to index again to guess, except we're actually just going to slice the array in half. So everything before guess can get thrown out, and we're only continuing with what's after guess. So if we take that, put it down here, in the next step we're going to be doing the same thing. We're indexing to the center of our array, and then we're going to store that as guess and check again, is guess less than our target? Well, let's say this time guess is actually greater than our target. So this time, instead of throwing out the first half, we're going to throw out the right half. And now we're left with each time a smaller problem. So it's just going to continue to do this until eventually guess is equal to target. So what you're seeing here is kind of like a divide and conquer type of method. Basically, every time we index into our array and check if guess is less than or greater than our target, we're throwing away half of the array, and therefore we're actually decreasing the size of our input by half and making the amount of problem solving that we have to do a lot less. So this function here is a demonstration of this binary search, where we're initializing our function with n, which is going to be equal to an array, and target, which is going to be equal to what we're looking for. And then what we're doing is we're saying, well, guess is not equal to target. we're going to index into the middle, store that as guess. If guess is greater than our target, then we're going to slice the list so that we're only going to the index of where guess was. And it's just going to continue to slice our list in half until we reach the number that we wanted. So if I run this, the first thing we got to do is create our array, which will start off just going from 0 to 10. And then call our function and give it search list, which is our array, as our input for n. And we're looking for 2. So when I run this here, you can see we start off with the full array. But then after we get our first index into the middle, we're going to be throwing away the stuff that is greater. Now this only works with a sorted array, but this is a good demonstration of O of log n because it demonstrates a logarithmic type time complexity. So you can see we start off with our full array, and then we have half, and then again we split it in half. And what I've done is just created a counter to demonstrate the amount of steps it takes. And you can see we also print out at the end that to verify that we've got the correct integer, which guess is equal to 2, and we've given it 2 as our target. But what's interesting really is to watch how many steps it takes as we increase the size of the array dramatically. So let's go straight from a 10 integer long array, or sorry, an 11 integer long array, all the way to a 100 integer long array. So it takes 8 steps, right? That's not as many as you would really think, because if we were doing this on O of n time complexity, this would actually take 100 steps. But what's cool is as it gets even larger, let's say 10,000, only 13 steps. And you can see what's happening each time it's getting split in half, the size of the problem, until finally we reach our answer. And basically, as this grows, you can see the amount of steps it takes is not growing that much. It's logarithmically related to the size of the input. So I think that's the best that I can really do to explain a couple of these basic time complexity expressions. There's a lot more online that you can look into these if you want more information. But the last thing that I want to talk about are some ways that you can simplify these time complexity expressions. So let me go ahead and delete everything, and we'll start off from scratch and show you 2 ways to simplify time complexity expressions. So basically, what you're looking at when you're talking about simplifying time complexity is you're looking at drop constants and non-dominance. So the first one I want to talk about is drop constants. So if we go back to our code editor, and I go back to my linear time complexity function, right now we're at O of n, right? Say that I want to do something like loop through n twice. So now our function loops through n once, but then it does it again. So you can see what's happening. We have our first for loop running, and then our second for loop running. But what I really want to convey in this idea is how this is handled with the expression. So basically what we have is one O of n time complexity and another O of n time complexity, which basically ends up being O of 2n. Now when we're looking at time complexity, what we're really concerned about is demonstrating how the amount of operations required is going to scale in comparison to the size of the input. And when we're saying O of 2n, that's not really, adding any benefit to, showing how the operations are scaling. Basically, we're interested in things that are going to dramatically change the slope of the graph that we're looking at. So this is still going to be a linear equation. And because of that, you can actually drop the 2 and make it just O of n. Now that is what you call a drop constant. The other thing I want to talk about is non-dominance. So if we have something like this for loop, but then we're going to say we're also going to add a couple operations on the end. So we're going to like, I don't know, print something, and then we're going to like do something like make a variable called x and make it n times n, print x. Right now what we're doing is adding a bunch of steps to this problem, right? But again, what we're focused on is trying to figure out how the size of the problem is affecting the amount of operations that we are required to do. And adding these three the print statement, the calculation, and another print statement, that's not really changing in response to the size of the problem. So this would be known as something called a non-dominant. And if we wrote this out in an equation, it would be something like O of n for original for loop plus 1 plus 2, whatever. So this, you can get rid of these 1 and 2 because they're not affecting how this actually scales. We're still going to have this O of n slope. And because of that, we're not concerned about these extra operations. So what we really will end up with, again, is O of n. So I hope this helped shed some light on this idea of time complexity. There's a lot more depth that you could give to this topic, and I'm still learning it myself. But I hope that, maybe you learned something today. And if you have any comments for me on some of the how I explain this, or if maybe I'm getting something wrong, just go ahead and leave that in the comments. But that'll do it on time complexity. So have a good day, and keep working.